Hey guys, welcome back to my channel. Today we're going to be talking about living worlds below. Now, when I was doing research for this video, I came across so many different theories and ideas that it was difficult to know what to include and what not to include. But if you do have any of your own theories, go ahead and share them in the comments below. And if there's enough interest in something, then maybe we can even expand on it into its own video. So go ahead and let me know what you think is down there. Also, while you're down there, please don't forget to like and subscribe because it really does help me out. Now, in general, this world consists of 7 layers. We have the first layer called the crust. Now this is where we live. This is the top layer and it extends all the way from the top of the earth, the surface, down to about 30 kilometers or 19 miles. The crust is also divided up into the oceanic crust, which is the bottom part of the crust, and the continental crust, which is the land masses above sea level. So both of these are part of the crust. The crust varies in thickness. It can be anywhere between 5 to 70 kilometers or 3 to 45 miles thick. Also, the crust is divided up into different plates that move around on top of the mantle. This causes the Earth's landforms to change over millions of years due to things like earthquakes and volcanoes. Moving on, we have the second layer, the mantle. This layer extends all the way from the bottom of the crust to about 2,900 kilometers, or 1,800 miles deep. The mantle makes up the majority of the Earth's volume and it is solid, but it behaves like a very viscous liquid over long periods of time. This means that, although it doesn't flow like water, it does move. This is how the tectonic plates move on top of it. Now the mantle is also divided up into different layers based on temperature. So we have the lithosphere, which includes the crust and the uppermost part of the mantle. This is rigid and it's part of the tectonic plates. Moving down, we have the asthenosphere. This is where the plates actually move on. It is less rigid than the lithosphere and it extends down to about 660 kilometers or 410 miles. Below that, we have the mesosphere, which is much hotter and it extends down to about 1,800 kilometers or 1,100 miles. Finally, at the bottom of the mantle, we have the outer core, which is where the Earth's magnetic field is generated by the movement of the liquid iron. And this will lead us to our third layer, which is the liquid outer core. Now, as I mentioned before, the outer core is made mostly of iron, nickel, and it extends all the way from the bottom of the mantle to about 5,150 kilometers or 3,200 miles deep. Now, although it is called the liquid outer core, it is actually a misnomer because it is not liquid. It is actually a highly viscous liquid. So although it flows, it does not flow like water. This layer is responsible for generating the Earth's magnetic field due to the movement of the liquid iron. This magnetic field protects us from harmful solar radiation. Now, moving down, we get to the next layer, which is the inner core. The inner core is a sphere with a radius of about 1,200 kilometers or 750 miles. It is surrounded by the outer core and it is located about 5,150 kilometers, or 3,200 miles. Deep within the Earth, the inner core is solid, despite being at a temperature of around 5,000 degrees Celsius or 9,000 degrees Fahrenheit. Now, this extreme heat and pressure keep the iron and nickel atoms from expanding, making the inner core more dense than the outer core. The inner core rotates slightly faster than the rest of the Earth. This creates a small bulge at the equator that is about 10 kilometers or 6 miles wide. The inner core is responsible for generating some of the Earth's magnetic field, but most of it is generated in the outer core. Now, when scientists have studied these lower layers, they have found some interesting things. For example, there seems to be some kind of a boundary between the mantle and the core. And there may even be a thin liquid layer between the two. Scientists believe that this could be a layer of molten iron sulfide. They believe that this could have formed when the Earth cooled and the iron sank to the core, leaving behind a layer of iron sulfide. Another interesting thing that scientists have found is that the inner core is not perfectly solid. There are some small areas where the iron atoms have been able to vibrate and move around a little bit. These are called inner core heterogeneities, or INCHs. Some scientists believe that these INCHs could be the result of small meteorite impacts on the inner core. Others believe that they could be the result of the Earth's magnetic field interacting with charged particles from the sun. Whatever the case, these INCHs are of great interest to scientists because they could provide clues about the Earth's history and evolution. As you might imagine, exploring these layers has not been an easy feat. Many of our current techniques rely on sending probes or instruments into the ground, or through the air, and recording the data that they collect. For example, we have used seismic waves from earthquakes to image the interior of the Earth. By recording the speed and direction of these waves as they travel through the Earth, we can create images of the interior. Another technique that we use is called gravity measurements. By measuring the Earth's gravitational field, we can create maps of the interior. This is because the Earth's gravity depends on the mass and distribution of the mass inside of the Earth. Now, these techniques have allowed us to learn a lot about the Earth's interior, but they are limited. We need to find new and innovative ways to explore the Earth's interior. One of the biggest challenges associated with exploring the Earth's interior is the extreme environment. Temperatures and pressures increase dramatically as you go deeper into the Earth. For example, at the core, temperatures reach about 5,000 degrees Celsius or 9,000 degrees Fahrenheit, while at the surface, they average about 15 degrees Celsius or 59 degrees Fahrenheit. These high temperatures and pressures make it difficult for instruments to operate and can damage them. Additionally, the Earth's magnetic field can interfere with some instruments and make it difficult to collect reliable data. But scientists are constantly developing new technologies that can withstand these extreme environments and make new discoveries about the Earth's interior possible. Another challenge associated with exploring the Earth's interior is the cost. Exploring the Earth's interior is an expensive endeavor. It requires the development of new technologies and equipment, as well as the deployment of missions to explore the Earth's interior. For example, drilling deep into the Earth to collect samples can cost millions of dollars. But the rewards of exploring the Earth's interior are great. New discoveries about the Earth's interior can help us better understand our planet and its history. Additionally, exploring the Earth's interior can lead to the discovery of new resources and energy sources. For example, geothermal energy, which is energy that is generated from the Earth's interior, is a renewable energy source that can be used to generate electricity. I want to talk about hollow Earth theory for a minute here. This is a theory that the Earth is hollow, and that there is a central sun at the center of the Earth. But this is just a theory. There is no evidence to support it. According to this theory, the crust of the Earth is a thin shell, and that the mantle and core are hollow. The theory also suggests that there are multiple layers within the Earth's shell and mantle, each with its own atmosphere and climate. Some versions of the theory even suggest that there is a civilization living inside the Earth. Now, this theory is not taken seriously by the scientific community, because there is no evidence to support it. In fact, there is a lot of evidence that contradicts it. For example, seismic data shows that the Earth is not hollow. The Earth's magnetic field would collapse if the Earth were hollow, and the Earth's gravitational field would be very different if the Earth were hollow. Alright, thanks for watching. If you enjoyed this video, please don't forget to leave a like and subscribe. And remember, don't be afraid to share your theories in the comments below. Until next time, stay curious.